Welcome, Lorenzo. I hope we have a better performance now. And Lorenzo is talking about 9-managed GKE, how they migrated from VMs to 9-managed GKE. So the stage is yours.
Hello everyone. My name is Lorenzo. I work with Kubernetes since 3 years, but I started to program with mainframes. So I work since 2 years in Comerge, and so we did a journey from virtual machine to Google Kubernetes Engines, and today we will explore the journey. So why and how we moved away from these virtual machines. So of course, first we had a problem, and we have an application, a chat application that is built on Spring Boot and is deployed on more than 40 customers on a Tomcat, Apache Tomcat application server. So in each customer a different number of users, from 10 to 5,000, so the size is quite different among customers, and they are located geographically in different places, so Switzerland, United States and Asia. And the number of users go down, but mostly grows in time. So we have to enable customers, new customer, install new customers, and also sometimes we have to decommission one. Everything was installed in virtual machines, so dedicated virtual machine for big customers, and as well shared virtual machines, so big machines with many customers deployed in one single application server, which of course leads a single point of failure. And among our customers we have also hospitals, so I will explain a bit in deep the problem what was. So on the left side we have customers, so they share a virtual machine, they have an application server and different application deployed to it, so from different sizes. The problem comes when just an application grows and the virtual machine is too little. So either we move the application to another virtual machine, the application is growing, the number of users is growing, or just for whatever reason they need more capacity, and then we have to restart either the virtual machine or we have to move it out. So in any case it will result downtime from the application 2 in this case, or for the old customer residing on the virtual machine. And also we can end up with this, so wasting resources with a big virtual machine and a tiny application of the. So anyway, we can restart the application, the virtual machine, but anyway, it will result in downtime. Okay, so to solve this problem, we have some requirements. We want to use better the resources we have. We don't want to waste. We need to be more flexible, improve the scalability, so when more users are coming in, so we need to serve them properly, and we want to avoid downtime and maintenance windows. We want to be a bit more independent from our providers, so where the virtual machines are not hosted but maintained, and we want to increase a bit the visibility, because at the moment the virtual machine has, if you want to look at the logs, you have to SSH on each of the 40 machines or 10 machines that they were. And also we would like to have a continuous integration relying on the infrastructure as code. So voila, the orchestrator is like Kubernetes is matching our requirements, so it should solve the problems. So for the resource optimization, first we will have we have the node autoscaling. So when new instances comes into play, they are scheduled. Then Kubernetes just watch if there is enough space and just create a new nodes Yes, it is a virtual machine, but it's also a node. And also we have the pod autoscaling or the pod scaling, so we can increase the number of the instances upon a code change. So as well, we improve the scalability. Like I say, the horizontal autoscaling is one, and now our application is fully scalable. So I will speak about later how we did make just an application scalable. So, and the deployment and the maintenance downtime, this was not really a big issue, but yes, it's always good to have an application which doesn't have downtime while deploying it and rolling it out, and when the virtual machine, the nodes are just upgraded. Then Kubernetes offers rolling deployment, which basically when our new release comes, it starts to spin up in a new pod, in a new instance. And then until this is ready, the old version still serves the request. And when the new version is ready to serve request, all the traffic is routed to the new instances, and the other one are just killed, terminated one by one. And this is good, and there is no downtime. We would like to be more independent, just ask less support requests for particular topic by changing the application server configuration, the memory settings, and so on. And also we want to, so by increasing the visibility, so Kubernetes offer the possibility to install Grafana, Loki, and Prometheus as a stream ingesters. So we have all the resources, metrics, and all the logs aggregated on it. So it's very easy to access them from a web browser and correlate them as well. It's quite tricky, but you can. And yeah, have a continuous deployment which is reliable. And we have now ArgoCD. At the beginning we didn't, but ArgoCD works very well for our experience. So now I will go through some points. First, regarding the node autoscaling, how it works. I just introduced that before. So just, it's an easy GIF here, but you can see that when the workloads put on Kubernetes increases, it just check, oh, there are enough nodes, then it just spin up a new node and places the new pods there, and you shuffle them among the old cluster node pools. And this is how it works there. So for the node upgrade, I took this GIF from internet, which it quite depict how a termination of a node works. So first we have the cluster, we have a set of nodes, and the nodes are distributed among zones normally. And when it comes to an upgrade, so how to avoid downtime. So in this case, just the node 1 is killed, it's terminated, it's drained, so all the workload of the pods, it's just shuffled, scheduled to another node, in this case node 2 and 3, and the node is shut down. And then a new node comes up with a new version of Kubernetes, and then all the workload will be scheduled there again. So this is also will avoid downtime during these upgrades. So at the moment we can have upgrades of the node without any downtime, which is very good. So then we are convinced, let's do it. Yeah, as Dilbert says, yeah, it's not that an easy journey. And yes, it doesn't solve all the problems, of course, it just also creates some others, but the quality of the software just increased just by doing this step. And okay, I will come later with the problems. Yeah, but what's the plan now? So what shall we do that what shall we do from virtual machines go into an orchestrator? So first we need to create a POC, proof of concept, then choose carefully the provider, the pro and cons and the performance. We'll come later about that. And also make it production ready. That's the real challenge here, because making a POC is quite, I won't say that easy, but yeah, it can have, so make it production ready, it's the real challenge here. And then afterwards, just slowly go into development environments, see how the application behaves, all the scaling and so on. And just rolling out until we had the first productive customers rolled out. So I worked previously with OpenShift Online for 1 year, and then for me I was just used to that, and so the POC was going to be there at first sight, and so we basically are the steps. So you put your Spring Boot application in the container, which was quite easy for us, was not that complicated. And we created a minimal resource kind specification without using Helm, just for the POC, just the deployment configuration of the application, an ephemeral database deployment just to hold the data, and as well the services to know how many pods are available, and also the root, so the reverse proxy configuration. You apply the resources and run it. Yeah, okay, it's not that easy as it sounds, but in 1 day we could accomplish that, and it was working. But the production road, it's a bit more difficult. So then second, after the POC was convincing us, so we just have to decide what to do. I was really an OpenShift fan, because it's easy to understand, and it's less complicated. But then we have to decide among both. We tested both, and we just also carefully evaluated each point here, and at the end of the day I was more for Kubernetes, vanilla Kubernetes, because of the numbers. And yes, then afterwards the managed offer of Google Kubernetes Engines won over, and the key points were so the cluster autoscaling. It's something that OpenShift let's say dedicated, so couldn't offer. We have to open service requests to have new nodes and scale up at the time, so scale out at the time. So for us was not really nice. And also we accepted the CD and CI integration, because at the time there was only a plan to introduce ArgoCD, and we just say, okay, let's do it with script. Horrible, but we did it. And after they delivered, it was very nice it's very nice still to use ArgoCD as a deployment help. Also, the learning curve, it's steep here, so in comparison to OpenShift, but Kubernetes is the foundation, so it's really worth to dig on that and to learn that, because yeah, OpenShift is anyway based on Kubernetes. So also OpenShift was at the time expensive, I think, because of the upgrades. And then we did some performance benchmarking, and somehow I don't know why OpenShift was slower. It depends on the machines or on the background, not from the technology probably. And yes, the POC is nice, but let's do it in production. So the way into production was quite long, and it took some time, some more iteration. And here I depict more or less the steps we took. So the first thing we did, then we had this this rudimental container deployable on OpenShift. So we have to change some parameters, and then was deployable also to Kubernetes. It was not an issue. And then yeah, we have to create Helm charts. So Helm charts, it's per se a challenge. Yeah, you have to put a grader on the screen just to indent correctly the YAML. But on the other hand, I had a very good documentation, so we could also learn a lot from this documentation. Just two hints I can give. It's like the parameterize everything you can on the YAML, on the Helm charts, on the templates, because you don't want to create a Helm release every time you need to change something. Just the more you parameterize, the more you're safe on new chart releases, and use fixed version dependency. So don't use the tilde. So try to avoid it, because we had an accident on development, and we just pushed a chart with missing dependency. No one complained, but the whole distributed cache went down. So just our suggestion is not to use that to get some special surprise afterwards. And also we use 3 separate repositories, one for the Helm charts, where the charts are released, for the templates are released, just for using just to be used from different customers as a reference, and also the infrastructure repository, where the values of each customer are defined there, and also a third repository where you put your application manifest of ArgoCD, that ArgoCD is able to know which application names in which namespace have to put and to manage. So second, after we have the Helm chart, we are able to deploy it. So I just present the CI pipeline we have right now, a big picture, not the one with the script, because it was horrible. Yes, first you build you check in the code, the new code, it's built, it's tested, and then with the commit hash, just build the image and tag it with the commit hash, that it goes to the container registry, Google Container Registry, and then afterwards this commit hash is just checked in the infrastructural repository, and then ArgoCD just go and grab the new revision of the infrastructural code, and then it says, okay, there is something which is not synchronized with the namespace, then I will apply the unsynchronized resources. And at the moment it starts, for example, a rolling deployment. So the new version of the software is rolled out and the old one is terminated when the new one is is ready and available. So here as well we have another repository. It's called the application manifest repository. So is where also Argo look for new customers, new application which are defined or which are deleted. So, and this application custom resource definition just point to the infrastructure of the application, so to the other repository. So ArgoCD can spin up and create the new application, the new resources, and synchronize the namespace. Okay, so then now we have a Helm chart. The Helm chart can be deployed upon new development, and yeah, ArgoCD is happy with that. So, and then now we have to make the application really scalable. So the next step was to remove the state of the application. Of course, the application had so the request of the application the requests were round robin. Yes, I don't know what to say. They used the round robin strategy to route the request on different instances. So one request is not really need a user session, but we have WebSockets, and each instance we have different WebSockets which are connected with the client. And also we have usually also scheduled task. It's just an operation that needs to be executed once per customer. So like let's say just lock the user which are expired. So you have to do it once. You don't want your 3 instances at the same time just to update the database. Will be a mess. So and then also we have memory caches. So how we solve that? Yeah, moving the caches is quite easy because yeah, Hazelcast, which is the technology we chose, because yeah, has a Spring Boot integration. It's well maintained chart, and then it's doing more than a cache. So moving the cache was quite easy. So usually there are maps on the application, and then you just change the implementation and that's done. The scheduled operation, we use the distributed lock. It's also a feature offered by Hazelcast. And yeah, when an instance start to update the users, then after all other instances cannot do the same operation because this operation is already locked. So this workload ideally should be delegated to a job, to a Kubernetes job, which is a cron job basically that does the work. But this kind of operation we have scheduled operation as not really CPU and memory greedy, so we decided to left it there for the moment. For the WebSocket, the story was a bit more difficult, but we used the distributed topic service of Hazelcast. So it means that a user just write a chat, push enter, goes to one instance from the reverse proxy. Just choose one instance. It goes there, it write in the database, and then it just publish a topic, and all the people involved on this chat will be broadcasted because all the instances read from the topic, and then knows exactly which device has to be notified with this new message. And then was quite hard work to make it this, but was really funny. And also and also the log files and the media. So our application just stores files, media files, and at the beginning we just used the network file system, and yeah, because it was transparent. So you write a file in your mounted folder on your container, and it just magically is available to all other instances. But yeah, turned out that was not really reliable, and we had kernel panics on one node one day, and another day on a node upgrade we get stuck with some, so the application was not able to write anymore on the file system. So we said no, we moved to Google Cloud Storage. A part of it's very stable, a part of the 13th of December. Yeah, we get quite a short surprise, but I must say that works well. Yeah, and also another point are the log files. So when the log files has to go away, because depending on the rotation policy that we put, they can take megabytes, 100, 200s, and one day the pod will explode and then will be restarted. So thanks to Grafana and Loki, now You just tap on the standard out of the container and we get everything ingested by Loki, and it's very nice. We have everything aggregated, we can read everything, we can search also through different customers. Okay, so now we have the application scalable. We removed all the states, all the file system that we write on the pod, on the container, sorry. And now we need to stress and to see what is capable this application on a tiny container. Of course, we just run into some performance issues because the application was written and was working on a virtual machine which is big, and actually we from the 6 GB of RAM that it used to run with, now we use 1.6 GB, and it's working well except for the thread. So when the number of users is huge, then it just increased the number of threads until the memory of the machine just crashed. So this was quite a nice lesson learned, how to handle out of memory killed from Kubernetes. But we solved that, yeah, eventually to make some other code which handled the number of threads and the capacity of the pod. Yes, after that, one of the most important part to go into the production is the monitoring. So a must is always to implement the container checks and like liveness and readiness, because we need to tell Kubernetes what to do with these instances. If we don't tell that an instance it's not healthy, it cannot process request, he doesn't know. But if we tell him, he can ask us, are you fine? Then Kubernetes will either stop the request for a short moment until we are healthy again, or just kill me because I'm not able to survive anymore. Then, of course, we can monitor with Prometheus all the metrics of the resources. So also Stackdriver offers us many metrics for the DB connection, the DB resources, how it's using them. Also we can see all the requests coming through the reverse proxy and so on, but this is just to monitor and see. So what's important for us is that the alerts. So we have alerts that are tuned on the inside the cluster, the health checks. When something is go wrong, we get notified. Most important is the pod restart, so we get notified when something restarts and the pod just doesn't answer anymore. And also outside with the New Relic, we get some availability checks that inform us if an application is not reachable from outside, and also we check the readiness of the nodes. So because sometimes the node just got restarted, they just killed, but Kubernetes is done for that. But we want anyway to be notified when some virtual machine of the nodes it's crashing, and also we ingest the logs as well. And everything is selected, so we have under control everything every time. So now we have also the monitoring, and just now let's nuke a bit the application. So I call it's chaos engineering. We do it in a soft way, not like other big companies, but the target here is to understand and know what your application is capable of in case of failure. So we have some scenarios that we do every time, sometimes. So we reach the state that if we delete a complete customer namespace and just recreate it, everything is there as before. So actually it's funny because once happened to me just to nuke a test instance, and then I recreated that, and someone was using that for a presentation just after 2 minutes that I restarted and reinstalled the application, and no one noticed something. So that was a good achievement. And also we just kill Hazacast instance, distributed cache instances. We delete application instances to see how the communication between the parts works. So we need to know that if someone is going down, is coming up, is reconnecting and speaking and shaking correctly, because we want to be able that the resiliency of our system is good. Yeah. And also, last but not least, also the node upgrades. So we need to be sure that when during the night there is a node upgrade, everything should work smoothly and we will have no downtime. For doing that, yeah, we need the pod disruption budget, just to tell Kubernetes how many pods must be ready, not starting but ready to serve request before to drain a node. So that guarantee a certain of service that avoid downtime, and also have redundancy, of course. So you need to have always more than one pod up and running. Yeah, another aspect to keep care about it after your application is stable and so on. So you need to size your node pools, your cluster, and so on. So that was quite a funny, nice decision to take at the end of the day, because yeah, the bigger the node it is, you can host so many pods, and Kubernetes is also happier that it can shuffle pods between nodes in a better way, so it can play Tetris better. But if you have smaller nodes, so if a node just explode or just got restarted, so the blast radius it's smaller. So if I have 5 pods running in a node and this node disappears, there are just 5 instances that are gone. If I have a huge node of 32 gigabytes, I have hundreds of pods running inside, then hundreds are gone. So when hundreds cannot serve anymore any request. And also another aspect to tune is the resource request. The resource requests of the pods are the minimal resources needed for this container to work. And this is very important to know the limit, because this is it just influences directly the cost of your infrastructure. So you need to test and see. So because Kubernetes just if you say you have 1 gigabyte of resource request, or no, 3 gigabyte, let's say, and you have a node that has 10, you can host at least you can host 3 pods, no more. So you have to be careful about that and put the right measure that your, for example, your application can bootstrap without problems. But the nice thing of the cloud is that you can try. So you just order some nodes, you make it auto-scalable, you schedule your pods there, and then you're fine. And you can just play with it. And the next day you can delete the node pool, and you know exactly what your application has a request needs. Okay, so now the journey is also finished. So the learning curve, yeah, there are many memes on internet about that, and it's really funny. It's steep, yes, for me as well, going from OpenShift to Kubernetes as a Java developer was like, ooh, it's a lot. You see behind the curtains. But after sometimes you get really used, and that it's not that difficult as it might seem at the beginning. And how we did overcome that, we organized some workshops, technical talks. We have some people inside the company that are enthusiasts like me, and we follow all the transitions. But the best way is to use it. So you cannot go deep so much if you don't use it. So that's my recommendation. So yeah, at the end of the journey, what we have. So I think I depicted most of the points, what we have now. So we are flexible for new customers which are coming, which are going, which are growing. So we have an infrastructure that keeps care that what we want is the desired state that we want is always strived to be there. We have our scalability. We don't have any more deployment and maintenance downtime, so at least the availability is there, and we are as well more independent on the deployment, and we have a good visibility. So at the moment we can really see everything, and we have the control on everything. So yeah, some pain points. Yes, writing the CI/CD pipeline deployment script with shell script and directly with Helm was a pain in the foot. Yes, in the feet. Also, yes, we work with Java, and Java and containers can be sometimes not best friends, and the tuning of the JVM, of the container, of the resources, and analyze the first kill, the first shoot we got from Kubernetes because the pod was just using too much memory or too much CPU. Yeah, we learned a lot on this path, but it's doable. So after you know how to tune it, it's really the same pattern at the end. And also, yeah, last but not least, the YAML indentation. That sometimes it's just yeah, going into nerves. So you need the scaler. Okay, so I think it's all from my side. Yeah, and we really enjoy to work as well. So the managed part, so how it's called, we are working with Mark, and it's really nice because it's yeah, with Nick and the guys, it's really good to work together. They are really competent as well. So thank you all. So we have, if anyone has questions, so how can I see the question?
Thank you very much, Lorenzo. There were no questions